Hi everyone, thank you for attending this webinar. My name is Claudio Mardegan. Today we are going to talk about special topics on ground fault protection and protection coordination. We are going to divide our presentation in 10 topics. Ground fault calculation, the importance of the correct calculation of the ground fault, system behavior as function of system grounding, escalation of single-phase arcing faults, types of coordination, coordination time interval determination, where to apply this coordination time interval, general rule and particularities, overcurrent relays, optimized settings, phase protection as backup of the ground single line to ground protection, coordination of voltage relays with overcurrent relays. The first part, we are going to talk about the ground fault current. The ground fault current, both single line to ground fault, is determined from doing a short circuit on phase A, and the boundary conditions are the fault phase, the voltage equals 0, and on the unfaulty phase, the currents are 0. In this situation, using the symmetrical components and replacing the boundary conditions on this equation, IB and IC is 0, so we are going to have 1/3 of EA for EA0. And IA1 is the same, with the same substitutions, you are going to have 1/3 of EA. And the negative sequence, the same value as well. So, we have 1/3 of the fault current as the sequence current. To have this condition, we have to put the positive, negative, and zero sequence circuits in series. And so all these impedances are series connected. And the determination of the current in this circuit is determined by this equation, the voltage divided by the sum of the impedance. The single line both ground fault will be 3 times the zero sequence current. In other words, we have to multiply the previous equation by 3. So this is the condition for bolted fault. ZG is the impedance between the neutral and the ground. Both single line to ground fault or solid ground systems, if we assume that the fault impedance is 0 and the system is solid ground, and for delta Y transformer, normally positive sequence impedance equals negative sequence impedance equals zero sequence impedance. If you do this assumption for a short circuit immediately at transformer terminals, what we're going to have is that if we substitute the Z0 by Z1, Z1 is Z1, and you Z2, all this little bit not so good. Okay, so ZG is the ground impedance, grounding impedance, and for solid ground is 0. replacing this value, you are going to have Z1, Z1, and Z1. Z1, and if we divide the 3 times the line to ground volt by 3 times positive impedance, we are going to have E divided by Z1. What we have is that the single line bolt to ground fault equals 3-phase bolted fault. This is valid only at the transformer terminals, because when you go down, the zero sequence impedance of the equipment will change this value. But immediately after the transformer terminals, single line to ground bolt fault have the same order of magnitude of the 3-phase fault, bolted fault. Single-phase arcing faults normally have a value lower than the bolted fault. And how lower it is about 30 to 90% normally. As a good guess, or good estimation, we can say that is about 50%. Normally, Dunk Jacobs present in his papers that the minimal probable arcing fault current is 38% of the bolted fault. And Mardegan and Mathieu, we have from 47 to 52%. For us, protection engineers, it's important to set our relays below this value. Normally, we use 35% of the single line to ground bolted fault. Now we are going to talk about single line to ground fault when we have generators in parallel with the utility. In this situation, what we have is the utility supplying this medium voltage switchgear through a 10 MVA transformer, and we have the generator supplying the same bus through a 2.5 MVA transformer. So the generator data is presented here, and the transformer impedance 0.6 and X over R are presented here. The positive sequence impedance are presented on the diagram. Converting this impedance to per unit on 100 MVA base, we are going to have this impedance calculated for the utility, for transformer 1, for transformer 2, and also for generator, and calculating also the generator resistance, we are going to have these values. So what the summary of this calculation of the generator impedance, we have these 3 values for the positive, negative, and zero sequence impedance. Now, you are going to simulate the first condition, that is the generator operating in island operation. In other words, you are going to remove the utility out of service. We can draw the positive, negative, and zero sequence circuits for this situation. We have the utility impedance in series with the transformer, and we have the second transformer and the generator. We are going to simulate a fault, a line to ground fault on the generator bus where this ray is indicated. So And applying a short circuit on this bus, because the utility is out of serve, I have no contribution from the utility. So I just have contributions from the generator. In this situation, the Thevenin equivalent impedance on the generator bus is just the generator impedance, sequence impedance. For positive sequence, for negative sequence, and for zero sequence. As showed before, the circuits are series connected. These impedances are series connected. And calculating this current, adding these three impedances and dividing 3 times the line to ground volt by the sum of the Thevenin equivalent impedance, we are going to have 0.2351 per unit. Determining the base current and multiplying by this value, we are going to have the single line to ground fault as 28,352 amps. So this is the hand calculation, and now we are going to calculate using EasyPower software, and first we are going to the short circuit focus, and I'm going to remove the utility out of serves, opening this breaker, and simulate a line to ground fault on generator bus. If I do this, we are going to have the same value that we calculate by hand. Okay? So now we are going to put the generator in parallel with the utility. In this new situation, we are going to have the sum of these 3 impedances, because we are going to have the contribution from the generator to the point of the fault and the generator contribution as well. So these 3 impedances are series connected and in parallel with the generator impedance for the positive sequence, negative sequence circuits. For zero sequence circuit, due to the fact we have a delta transformer here, I don't have zero sequence contribution from the utility, so I'm going to have just a contribution from the generator. Now we have to determine the Thevenin equivalent impedance at generator bus for positive, negative, and zero sequence. Doing that, we have to put all these circuits in series and determine the Thevenin equivalent impedance. Calculating this Thevenin equivalent impedance that are presented here, taking these values and moving to the equation, we are going to see that the total bus fault will be 66,301. So let's go to EasyPower again. Now I am going to close this breaker, and the current at the bus will be 66,301, the same value as hand calculated. So what we are going to see now is the generator contribution and the system contribution. In this situation, the contribution is calculated by the sums of the opposite impedance, system contribution, divided by the sum of all the impedance, multiplied by the total current. That's the value that we have already calculated. Okay? So, you do the same calculations, and we are going to have 28,311. For generator contribution, this is system contribution. Generator contribution, if we substitute the impedance, we are going to have 38,002. This is the hand calculations. So, if we come back here, we are going to see that the system contribution matches with the hand calculation, and the generator contribution matches with the hand calculations. But what we intend to show here is not the hand calculate match with the group. The big problem here is that the neutral current on the generator will be the sum of the phase currents. The meaning of that is we are going to have 66 kiloamps flowing in the neutral. And normally, people, when is sizing the neutral conductor, they take only the generator impedance to determine that. And this is not true. This value is higher, this value we calculate here is higher than the simple calculation of this very simple method of using the generator impedance. So it's very important to perform the simulation and sum the currents of the three phases. If we sum this, the angle is practically the same, and you see that the value will be very, very high. So the total bus, the calculated and simulated are the same. This is very important. The conclusions about this simulation is that the ground fault current may be greater than the three-phase short circuit current. Let's see. We come here. If we change from line to ground fault to three-phase fault, we are going to have 58 kiloamps. For line to ground fault, we have 66 kiloamps. So the value is higher than the three-phase fault. And in the neutral, the current will be very, very high as well. The ground fault current with the generator operating in parallel with the utility may be greater than the single line to ground, and in this case of this example, it is. The current in the generator neutral for the parallel condition between generator and utility is greater than the single line to ground fault current for the condition of the generator in island operation. This is very important also for the power system analysis engineer. Engineer has to be aware when sizing neutral conductors for generators. And protection engineer has to be aware with the current they are taking into account when setting the grounding relays. Because if your relay is in the generator neutral, your relay will see this big value of short circuit current. Another very important problem that normally it's the first time I faced this problem, and I was a little bit surprised because when you mix different types of system grounding, what I mean is, if your transformer is low resistance grounding and someone connects a generator on the same bus, solidly ground, what we are going to have is that if our generator is out of service, the total ground fault is practically determined by the resistor, neutral resistor. But when we parallel both, the line ground fault will raise a lot. And also, the generator contribution will be very, very high. In this case, the bus short circuit current is more than 10 times of the line to ground fault for the condition the utility operating without, and the generator is out of service. So we can explain the situation by the zero sequence, by the sequence circuits, because the generator zero sequence impedance normally is very, very low. When I parallel this generator impedance with system grounding impedance, the value of zero sequence impedance will be very, very low. And the same here for the generator in parallel with system. These two impedance, positive and negative sequence, will be lower than the lowest of this impedance. That's why the system is calculated. We can also go to here and simulate the situation with the generator out of service and now I'm going to short circuit focus. For a line to ground fault we have practically 400 amps. But when we put the generator in operation and we go to short circuit focus, we are going to have a very, very high value. In the part 2 of our presentation, we are going to talk about the importance of the correct value of the fault current. For a protection engineer, the most important thing is that the calculated value be as close as possible of the actual value of the short circuit. This can be determined watching the relay oscillographies. And for this parameter, you can understand if your short circuit calculation was well done or not. And when the calculated short circuit equals the actual value, our coordination time interval that we applied to perform this chronological coordination, it's okay. But if we use a short circuit current value higher than the actual, so the actual is this one, and we use a higher value of short circuit calculated, the calculated is higher than the hand calculation, than the real, than the actual. So the time we are going to have a higher time. So if our calculated short circuit is higher than the actual, when the short circuit happens, we are going to have a higher value of time. So the coordination time increases. When it happens, we are going to have more damage and more time to system return to operation. This means a loss of production. Another situation, when you have calculated short circuit lower than the actual value, means that if a short circuit happens, the short circuit value will be higher than yours. So you can have miscoordination because the coordination time interval will be lower than that one you have designed for the system, used for the system. Another important issue that we talked about that was using the arcing fault on our TCCs are very, very important, because normally the coordination time interval is applied for the bolted fault. That is this TCC in the on the left, right? But when we have an arcing fault, we were not going to have a bolted fault, so the value will be lower. So you come to the TCC and we mark the arcing fault on the TCC. In this first situation, for a bolted fault, that in this region, we are going to have about 400 milliseconds to trip the upstream relay. But if we have an arcing fault, because I am using an inverse time relay, the relay will trip in 698 milliseconds. So now we are going to apply some optimizations technique, setting a second element of our overcurrent relay. The meaning is that for bolted fault, our upstream relay trips on 400 milliseconds, and also for arcing faults, our protection will trip for the same time. Any current in this range from the arcing fault to the bolted fault will be removed at the same time when we use the second element with definite time. In the third part of this presentation, we are going to talk about the behavior of the electrical power system when we ground our system, thinking that this system is low resistance grounded. But in fact, sometimes our system may not be low resistance grounded. This example is based in a real case that happened here in Brazil, in a paper mill plant. And the plant is a big plant with long cable runs. And what we have is something that I'm going to show you on the next slide. But first, we have to understand that the threshold of a system be considered ground or not is defined by system stray capacitance. The meaning of that, when we select a low resistance ground system, the resistor current shall be less or equal 3 times, shall be higher or equal, greater or equal than 3 times the total charging current. This charging current is determined by the sum of all capacitance of this level of voltage. In this slide, we can see the system. It's a 9 MVA transformer, and the design engineer chose a low resistance ground 100 amps resistor with a 100 amp resistor. So in this the outgoing feeders are long cables. I have cables of many sections, cross sections here. And here is the capacitive reactance of each type or each size. And we have also the transformer's capacitance downstream our cables. And we have also the capacitance of the power transformer and the switchgear. The cables for each circuit, we have the cable length and the number of conductors per phase. And the capacitance are calculated dividing the reactance, the capacitive reactance of the cable divided by the length and divided by the number of conductors per phase. And the capacitance is calculated using this equation. This was performed for all the outgoing feeders, and we got almost 6.7 microfarads. If we sum the cable capacitance, the transformer's capacitance, and the switchgear capacitance, you are going to have the total capacitance. And with the total capacitance, you can calculate the capacitive reactance of the charging of the system. And we got 380, almost 87 ohms. The current is determined dividing the voltage, the line to ground voltage, by this capacitive reactance. And we are going to have 51.5 amps. The 3 times IC0, that is the threshold between the system being considered grounded or not, is 154.5. That's greater than the resistor amps, 100 amps. So we think you are low resistance ground, but in fact we are not. Our system will have the behavior of an ungrounded system. This kind of practice of calculating the stray capacitance on the system before determining the resistor size should be implemented on our guides and our design, and in order to the system be adequately designed. Escalation of single-phase arcing faults. This subject normally is it's not very well treated by engineers. There are very few papers with this subject. The one I found is from Mr. Duncan Jacobs, and what he says is that for a low voltage system, when normally the bus bars are not insulated. So the problem is that it's easier to have the escalation from a single phase arcing to a biphase and three-phase. For medium volts between 2.4 to 7.2, the registered events normally in the register events the bus bar was not insulated, but from 13.8 to 34.5 kV, normally all the bus bars are insulated. Okay, so the probability to have escalation is difficult to happen. But if you have aerolines, normally the fault can escalate between from 1 to 2 cycles. It's very, very fast. The escalation happens very, very fast. Types of coordination is part 5 of our presentation. The main types of coordination are the chronological coordination, current coordination, and zone selective interlock coordination. The chronological coordination is the most known and everyone knows because that one used on our TCCs, and we use a coordination time interval between the downstreams and the upstreams relay in order to get, if a fault happens, the downstreams relay will trip before the upstream relay. So the first relay, if it trips in 250 milliseconds, we choose a coordination time interval of, for instance, 250, and our second relay will trip after the first one, 250 milliseconds. This coordination time is called chronological coordination. The current coordination is normally used when the short circuit current between the downstream relay, the difference of current of the downstream relay to the upstream relay is very, very high. Okay, so the problem is that when we have this big difference, and this big difference caused by the transformer impedance, we can set the instantaneous element as a second element of the primary of the transformer. Normally, when we have transformer has a big impedance, we can use this current coordination. The meaning of that, when we use the coordination in 13.8 kV, is referred to 13.8 kV, a short circuit on low voltage system will be 33 kiloamps. Referred to the primary side will be 1.1 kiloamps. That's the value indicated on the primary side. So this downstream relay is seeing 33 kiloamps. In the same time, our upstream relay is seeing 1.1 kiloamps. So if we choose coordination timing interval for short circuit on the secondary side, the timing element will be coordinated with the secondary side relay. But the highest short circuit current on the secondary will be the first cycle of symmetrical short circuit current. After the short circuit current, the short circuit will be not anymore on the secondary side, but on the primary. What we do is to set the instantaneous element 10% higher than the maximum asymmetrical short circuit on the secondary side. This is called current coordination. The big advantage of using this is that when I set instantaneous here, our coordination time is resetted. We can start counting the time again. In other words, the upstream relay above our primary relay, I can choose the coordination time interval above the instantaneous time. And we have also the selective interlocking coordination. Normally, what we have is that when a short circuit happens at point A, all the three relays are going to see our short circuit current. The pickup of the closest to the fault relay blocks the upstream, the immediately upstream relay, and this second relay blocks the upstream relay, and so on. Okay. The only relay that is not blocked is our closest to the fault relay. And so all of them are counting the time, but the only that is going to trip is the closest to the fault, because it's not blocked. If this relay trips the breaker, after a time, if the relay is still seeing a current, means that this breaker did not open. So the blocking is removed, and the brake failure also will send a trip signal to the upstream breaker. And also this relay that had already counted the time will trip again. The coordination time is the sixth part of our presentation, is the coordination time interval. That's fundamental to guarantee that downstream protective device is going to trip before the upstream device. We have to take into account all the variables that can interfere between the operation of the downstream relay and the upstream relay. Normally, what affects the elements that interfere on the coordination time interval are CT errors, but normally CT errors, they interfere in inverse time relays, but not for definite time relays, because the pickup, the definite time element, the trip time is always the same, despite the relay errors. It's also important circuit breaker interrupting time, because on the TCC the relays represent just the time for the relay operation, but not of the circuit breaker operation. So it's very important, the interrupting time. Protective device pickup error is the error of the device, and the delay error is also the delay. And we have also for low voltage breakers, is a little bit different from the relays, because the time you see on the TCC for a low voltage breaker is the total time to trip. In other words, is the time for its relay counting the time, is the trip to open the breaker, is that the trip that interrupts the current and interrupts the arc. So all of these times are included on the TCC. And the protective device time current characteristics is also important for determination of the coordination time interval. I told you that inverse time relays are affected by CT errors, and definite time relays are not affected for them. IEEE STD 242 is the buff book, suggests a table that's presented here. We are working on this chapter right now. I guess that some people that is part of our working group is also attending our presentation, and we are working on this table. Why? Because here there are a lot of small tricks. Because here you say between the static relay, we have to static relay. With static relay, you shall use 200 milliseconds. Here doesn't say if a relay is inverse time or not. Doesn't say if the relay is directional or not. Normally, what I can I could see doing testing the relays, when the relay is a directional, has directional elements, the time to calculate the direction is higher. And normally, one relay that normally calculates until it trips an overcurrent relay is about 32 milliseconds to do this. When directional element is used, would take about 72, or in other words, about 30 to 40 milliseconds more. So we have to discuss this table a little bit more. Another issue is that circuit breakers, for instance, here, with low voltage breaker with low voltage breaker. The standard says that this guide says that you have to see a clear space between the curves. In other words, the highest curve of the downstream device should have a big space to the lower curve of the upstream device. This is not always true, because some manufacturers can guarantee that even if the curves touch themselves, they can guarantee full coordination. Some manufacturers have softwares that automatically says this to you, but others you have to consult them. And the big problem is when you use different manufacturers. So in this case, here the curves are touching. We don't have a clear space between them. But this manufacturer grants to us that here we are going to have full coordination. And this is very important for when you are doing a coordination study. What we can do, the problem is that when you have devices from different manufacturers. So the way to guarantee is testing. If you don't have how to test, so you have to use a clear space. Okay, it's my suggestion. Where to apply in the part 7 now, we're going to talk about where we should apply the coordination time interval. The coordination time interval, the main role is coordinate the downstream relay with the upstream relay at the short circuit current. Okay, so you are going to apply the coordination time interval for the short circuit current. That's the main role. Let's go to the particularities. The first one, there are many particularities, but because the time we have is not so big, we are going to talk just some of them. Here, I'm going to show you when you have two income feeders and one outgoing feeder. You may say that this situation doesn't happen frequently, but I can tell you that always happens this when you have a switch gear or MCC that you have a tie. Every time you close the tie, you have the situation. You have two income feeders, and each outgoing feeder is one outgoing feeder. So the situation is more common than you expect. Here, what we have, a short circuit on the outgoing feeder. Our closest to the fault relay in this outgoing feeder is going to see the sum of the contributions of the two income feeders. Where should we apply our coordination time interval? We shall apply the first, the role of the thumb of the coordination is used always the current that each device sees. So the first device is seeing the sum of these two currents. But the upstream devices are seeing currents that are lower. So we have to apply the coordination time interval not just for the same current, but the current that each one is seeing. I prepared a small example here, putting the same pickup to all relays just for academic reasons, not to take so much time. So I use 100 amps pickup for relay 1, 2, and 3. And I'm going to use an IEC very inverse time curve. The equation of IEC standard for the very inverse curve is this one. I can take the time dial, and to calculate the time dial is T multiplied by M minus 1 divided by 13.5. What means M? M is the multiples of our pickup setting. So the relay 1 is seeing 2000 amps and its pickup is 100 amps. So the multiple of our pickup setting will be the short circuit current divided by the pickup amps. In this case, 20. The first relay is supposed to trip in 250 milliseconds. So if you substitute these values in this equation, we are going that the relay 1 will trip using the time dial of 0.35. I do the same for relay 2. Relay 2 is seeing 100.2 kiloamps, and in other words, it's going to see 12 times its setting. To coordinate, I will add 0.25 milliseconds. 0.25 milliseconds. So I have already 25 milliseconds plus 25 milliseconds. We will have to trip in half a second. Applying the calculated values, the time dial setting will be 0.41. For relay 3, we do the same, because the time to coordinate with the downstream relay has to be 0.25 milliseconds. So I'm going to use 0.25 milliseconds. And the multiples of the current that this relay is seeing is 800 amps divided by the pickup setting, 8 times. And the time dial is 0.26. Now we are going to have the surprise. The surprise is that if we go into the TCC, we see that the curve of the relay 3 is below of the relay 2 on the TCC, and the relay the relay 1 and the relay 2 is just a little bit above the relay 1. Watching this curve, those ones that are not normally used to do TCC, they are going to see that the system is not coordinated. And I can grant to you that they are. Because when a short circuit happens in the outgoing feeder, the first relay are seeing 2000 amps, and you take 0.25 seconds to trip. At the same time, the other relays are seeing the same current, and they are going to trip in 0.5 seconds. So they are coordinated. You see? So what I can tell you that in coordination, sometimes what you see is not what it's happening. So you have to pay attention in these particular situations. Another case, a particular case very interesting, is that when you have a delta Y transformer and line-to-line fault is applied to the secondary side. When this happens, on the primary side, we are going to have 1 divided by root 3. In one winding and on the other winding. This means that in the incoming winding, we are going to have 2 times the value of the one winding. But this means also that we have 2 divided by root 3 times line-to-line short circuit. But line-line short circuit is root 3 divided by 2 times 3-phase short circuit. In other words, if this root 3 cancel with this other, and this 2 cancel this 2. The meaning is that if we have a line-to-line short circuit on secondary side, in one phase on primary side, we circulate the value of the 3-phase short circuit. The meaning is also that the secondary side relay is seeing a B-phase short circuit, and the upstream relay is seeing 3-phase short circuit. So the coordination time is not applied to the 3-phase short circuit, but between the B-phase for device 1 and the 3-phase for the device upstream. This is a very important situation. Overcurrent relays, in part 8, we're going to see overcurrent relays optimized settings. Here, what we have here is phase protection. Okay, so we have a circuit breaker. If someone is performing a short circuit study and also coordination study, you receive this TCC. Is coordinated? It is, because for the single line to ground both fault, here is not both. I apologize. It's a 3-phase fault. If you have a 3-phase fault here, you are going to see that this coordination time interval, they are respected. So you have coordination. The big problem is that if we have a 3-phase arcing fault, this relay it will take longer to trip. So what we do is to set a second definite time element in order to make the relay trip faster. And the gain we have for the relay 1 is this one. For the device 2 is the green one. And for the blue one, the gain we have is this one. This means trip faster, and we can protect a little bit more also the personal equipment and the process, because as faster is our trip from the relays, less the damage we have on the system, and less the time to repair. For ground protection, we have also normally the ground setting of the circuit breaker. You have also the inverse time relay. It's the same situation. What we do is that if you have the single phase arcing fault here is very important. Another important thing is that IEEE 1584, when it says arcing, is always three-phase arcing. But here, in this case, I am saying of single-phase arcing. That's different from three-phase arcing. Okay? So, here, what we do is to set also a second element below the single-phase arcing fault for the first device and for the upstream device. In the same way, we gain some time during the short circuit trip. Okay. Overcurrent relays, optimized settings. Here also there is a small problem. If you receive a TCC with these curves plotted, someone may think they are coordinated. If you look here, seems to be coordinated. Because here I have the coordination time interval. The only problem we have is that the first element of the upstream relay is an inverse time element. And the upstream, the second element of the upstream relay is a definite time element. These elements, they are independently one from each other. They count in the time independently one of the other. So, this inverse time relay, it's counting the time. The TCC program cuts the curve when you put the second element, and you think it's coordinated, but in fact they aren't. So it's very important to take care when you use the second element as a definite time element. Okay, I would like to show you something more, but our time is going. So we are about to finish, but just to show you 2 slides more. Phase protection as backup of ground single line to ground protection. This is also very important because if we do the techniques, you apply the techniques of a second element of definite with definite time. If you do that, the way you have to have the phase protection as backup of single line to ground arcing fault is using on the phase TCC the single phase arcing fault and setting the second definite time element below this single phase arcing. If we do that, our phase protection will work like a backup protection of our ground protection. Okay? And the last part of our presentation is the coordination between voltage and overcurrent elements. When we have solidly grounded systems, normally we set our voltage relays about 115% of the rated voltage using 2 seconds, and the instantaneous 120% of our rated voltage with no delay, instantaneously. But if our power system is high impedance grounded, when a line to ground fault happens, the voltage on the unfaulty phases will raise, and we cannot use instantaneous anymore to trip, because if we do that our substation operator go to the annunciator and it sees that it was just an overvoltage, because if we set instantaneous, our voltage relay can trip before our overcurrent relays. And he thinks there is no fault, just an overvoltage, a normal condition. And he switched on a fault, and it's unsafe. So in this situation, what we have to do is setting our relay to trip for 115% of the rated voltage using 3 seconds and 122 seconds. The 2 seconds because normally our overcurrent relays have to trip before 1 second, is to guarantee that it won't trip again. So, people, thank you very much. I would like to apologize for the initial presentation that on my screen it seems that my screen was on air and it wasn't. And thank you very much for attending, and I'd like to apologize for that. Okay, thank you very much.